Okay, let's look at 7.5, modeling data using logarithmic functions. Your last section of grade 12 applied math. Yay! Anyway, so this is found on page 488 of your textbook. Once again, we'll just flip to the last part, which is your summary, and then it gives you your key ideas. So like every other section in 6 and chapter 7, it's the same idea. We're going to go plot some data. We're going to get a regression model, which is an equation, and then we're going to use the equation to solve other questions, right? Okay, so a logarithmic function may be a good model for a set of data if the points on a scatter plot form increasing or decreasing curve where the domain is restricted to the positive real numbers. Okay, so you need to know the general form of the logarithmic regression is a constant plus a multiplier times the ln natural log of x. Most graphing calculators and spreadsheets provide the equation of the logarithmic regression in the form of a plus b ln of x. We'll talk about that when we do an example. And a logarithmic curve of best fit can be used to predict values that are not recorded or plotted. So that's, again, that second part of the question. Once you get the equation, you're going to use it to predict. You're going to interpolate or extrapolate the data depending on what the question is asking for. Okay, so this is a little different than what we looked at in the last section, but it's just showing you that there's different ways to write this equation, and if you need to write the equation in that way, then you know that it exists. Okay, so we'll look at what our graphing calculator does. So let's go to example 1 so you can follow along. So that's on page 489 of your textbook. So the flash on most digital cameras requires a charged capacitor in order to operate. The percent charge, big Q, remaining on the capacitor was recorded at different times t after the flash has gone off. Okay, so the percent charge to the time it has gone off. The T5 flash duration, or the T flash duration, represents the time until a capacitor has only 50% of its initial charge. The T.5 flash duration also represents the length of time that the flash is effective to ensure that the object being photographed is properly lit. So construct a scatter plot for the given data, determine the logarithmic function of the model, and use your logarithmic model to determine the T5 flash duration for the nearest hundredths of a second. Okay, so let's go to our graphing calculator. We're going to go to the stat, we're going to go to enter, and we're going to enter the data. Now, how are we going to enter the data for this one? Because usually time is our independent, right? But this one, time is going to be our actual dependent variable. So we're going to go and we're going to clear our lists. You should know how to do this by now. Go up, clear, hit down. So our first one is 100%. We're going to go down. Our second one is 90.26. And then 73.90, 60.51, 49.54, 40.56. Enter. Enter, go across. 0, 0.01, 0. Enter. So what do I do now? To create a scatter plot, I go to y equals, I clear the equation that I have, I go to second function, scatter plot, I hit enter, where it's blinking on, I hit enter, and then I go to graph the equation. Okay? Nothing's graphing. So obviously it's not within this range, so I'm going to have to figure out the range. So if I go to my window, I'm going to look at my minimum value for x. Well, it's lower than 40, so, or pardon me, around 40. My maximum is 100. My scale will make 5, just so I can fit it on the graph. my minimum for my t is, or y is 0, and my maximum is like 0.1. I'll keep it on the scale of 1. I don't really see it yet. Okay, oh, there it goes. Okay, so I'll go to my graph, and it'll show me my logarithmic regression. If I look at the logarithmic regression, it's obviously decreasing, right? Okay, so now I go into stat again. I go to edit, pardon me, I go to calculate, and I look for which regression. Now if I look at all my choices, I have a cubic, a quad, quartet we won't use, I have a linear, and then I have an LN regression. I don't actually have a log regression, okay? So the only regression that you can use is your LN regression, okay? So I'm going to hit enter on it. I'm going to go down to it, and I'm going to hit enter to calculate, and I'm going to wait for the graph, and then it's going to spit me out a value. So the calculator writes it as follows. So it'll be y equals a, which is 0.46, or 0.4597, if you want to use that, minus, because b is negative, 0.0998 to the ln of x. So if I go back to my original question, I constructed my data plot, check mark, determine the logarithmic model. Remember, model is equivalent to equation. So y equals 0.4597 minus 0.0998, the ln of x. And it says, use your logarithmic model to determine the t5 flash duration to the nearest hundredth of a second. Well, I want to figure out what was t5. T5 was when my capacitor only had 50% of its charge, right? Okay, so I know it's going to be around 0.07 anyway. But since that's the y of the graph, we could do what we did last section. I can go back to my graphing calculator, and I can draw, I'll put my linear regression in, or my logarithmic regression equation in first. So I'm going to put my 0.4597, subtract 0.0998. I'm going to hit the ln button, and then I'm going to hit x. Okay, then I'm going to put an n bracket. And then I'm going to go down to the second one, and I'm going to put a y equals 50 so I get a constant line. And then if I graph this, we'll see what I get. And then I can do my intersections again. And hopefully the calculator won't freeze like last time. Okay? Where's my line of 50? So I go back here, go to my second one. It should be at 50, right? So where's my curve? So it's not doing my line at 50 for some odd reason. Okay, well, I can use my cursor, and I can go roughly down to, oh, pardon me, that was my x value. Sorry, that's what I'm getting confused at. That was my x value. So I could just go second function trace, I can hit value, and then I can hit the 50, and I can hit enter. I'm so used to time being the independent that I forgot. So it tells me roughly at 0.069 or 0.07, right? So if I go back to this, and I'll just answer to the nearest hundredth of a second. So that's 2 spots, so it'll be y would equal 0.07 seconds. Okay? So that's pretty much it. We'll do a couple more just to make sure you're comfortable with it. So caffeine is found in coffee, tea, and soft drinks. Yeah. Many people find that caffeine makes it difficult for them to sleep. Caffeine actually elevates you, then you hit a huge crash because it's technically a depressant. But anyways, the following data was collected in a study to determine how quickly the human body metabolizes caffeine, which means breaks it down to get rid of it, right? Each person started with 200 milligrams of caffeine in her or his bloodstream, and the caffeine level was measured at various times. Okay, so you get this big chart of data. If you notice, these two columns keep repeating and repeating and repeating, right? So it's a lot of data to enter into our calculator, but it's the same question, right? So determine the equation of the logarithmic regression for the data, determine the time it takes the average person to metabolize 50%, and then Paula drinks a cup of coffee, right? So I'm just going to go to my graphing calculator. I'm going to go to my stat. I'm going to my edit, and then I'm just going to pause the video, and I'm going to enter all these values in so you see how I get this example. So this example is on page 491. If you just want to pause the video too so you can enter in the data. There is no quick way to enter the data. You just have to enter the data into the graph. Okay, so this one doesn't ask you to make a scatter plot, but you still can if you want to. So you go up just to make sure you did the right thing. You clear your equations. You go to second function. The plot should be on. Go to zoom 6 just to see if you can actually see the data. Okay, you know it's actually decreasing. You can see that. So it's not showing in there, so I have to go to my window. My window is my X, so the least amount of caffeine looks like around, the least amount's around 15, so let's just make it 10 to be safe. Okay, and then our X max is how much? So it's 200 that they took. Okay, our scale, let's make it at least 20 so we can actually see it on the graph. Our Y minimum is our time. It looks like 1 is the lowest, so let's keep it at 0. And the highest time looked to be about 19, so let's make it about 20. Let's keep that scale maybe at a 2. That's too short, that's 2. Let's make that a 1. Okay, and then you can actually see your graph if you graph it, right? So there's your scatter plot. If I go to stat, if I go to calculate, and I go down to my LN regression, or just hit 9, and I go hit enter again to calculate it. Okay, it's thinking. It's going to give me the equation right away. So your equation is y equals 44.393 plus, or pardon me, minus, because b is negative again, negative 8.3577 ln of x. Okay, you're going to take that and you're going to type it into your graphing calculator. So 44.393 subtract the 8.3577, the ln of x, hit your end bracket, and then you can graph that as well. Okay, so then you can answer the questions from the book. So the book says, determine the logarithmic regression. So we did. It was y equals 44.393 minus 8.3577 ln of x. Okay, determine the time it takes an average person to metabolize 50% of her caffeine. Everybody started at 200, so 50% of that, we're looking for the 100 milligrams. Remember, x was your milligrams. So just going to your graphing calculator and typing in second function trace, hit enter, and hit 100, and enter again. It's about 5.92 hours, right? Or pardon me, 5.90 hours. Okay, so let's go back here, and we'll put in our x equals 1/10 of an hour. So 5.9 hours. Okay, and then C is Paula drank a cup of coffee that contained 200 milligrams of caffeine at 10 a.m. How much caffeine will be in her bloodstream at 9 p.m. that evening? Round your answer to the nearest milligrams. So we have to figure out the time difference there, right? So what's the time difference between 10 a.m. and 9 p.m.? So 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9 gives you 11 hours. Okay, so y would have to equal 11 hours in this example, right? So like we did before, like I got mixed up again, if you go to y equals, and you go to down and you type in 11. You can go to the graph and it'll put a line in at 11, and then you can find the intersection of those two lines. So if I go to second function trace again, I'll hit number 5 for intersect. My first curve, I'll hit enter. My second curve, I'll hit enter. It'll say guess with a question mark. You just hit enter again, and it actually worked this time. Yay! So after 11 hours after drinking a cup of coffee, Paula will still have 54.4 milligrams of caffeine left. So 54.4. Okay. 0.4 says milligram. Okay, so make it 54 milligrams of caffeine left in her bloodstream. Okay. And that was it. So your practice is page 495, 1469. So what I suggest, if after doing this and working on the textbook questions, if you're still feeling uncomfortable, I really, really like the workbook. It's pretty straightforward in the workbook for chapter 6 and 7. So if you need a refresher, I would definitely go into the workbook and work on some of the problems there. Okay? Every logarithmic and every exponential and cubic and linear and quadratic regression I've seen modeled on the tests are just, you're given a set of data, you plug it into the calculator, you have to do a scatter plot, you kind of determine the line of best fit to see what it looks like, and then you do a bunch of linear or a bunch of regressions to figure out which equation best fits the line, and then graph it on the line. Okay? So if you want an example, maybe we could go over the one from last year's exam that I gave you now that you've watched these videos, and it'll show you a great example. So good luck.